I'm pleased to welcome Manoo Shirzaei to the podcast. Manoo is an associate professor of geophysics and remote sensing at Virginia Tech. And today we're going to talk about land subsidence in various regions that Manoo has been studying, and mostly related to overexploitation of groundwater in semi-arid regions like Iran, California Central Valley, and Arizona, and then also impacts of land subsidence on relative sea level rise in coastal areas. And Manoo will also explain, I think, many of the new tools that are available that has advanced monitoring of land subsidence and other aspects related to it, including gray satellites, GPS, and INSAR, and modeling analysis. So thank you so much, Manoo, for joining me today. I really appreciate it.
Thank you for having me. It's my pleasure and honor to be on your podcast, Bridget.
Right. So, Manoo, we've known each other for a few years now, and you grew up in Iran, and there's a lot of discussion about overexploitation of groundwater in Iran. And I have seen people have sent me images in the past of fishing and stuff from land subsidence in different regions. And people have applied gray satellite data to look at groundwater depletion and also monitored land subsidence. There have been a number of papers recently published on land subsidence from INSAR, interferometric synthetic aperture radar data, and also GPS data. Maybe you can describe that a little bit, Manoo, from your experience and also from what they're saying in the literature.
Yes. So Iran probably is the hotspot of land subsidence at the global stage because of, it made it to the media in recent weeks, as a matter of fact, that shortage of water, surface and groundwater, is at the level that countries approaching the water bankruptcy. Fortunately, in past weeks, we had some rain and snow that brought us slightly away from that 0 day, but by no means situation has improved in the country. So over the past several decades, confluence of several factors resulted into significant shortage of water that has impacted all sectors of the society and economy as a whole. One key driver, obviously, is the climate change. Large part of the Iran has become very dry, while some other parts became extremely wet. And that has created this opposite hazard in different years. So one year we have a massive flood that submerges cities and unfortunately causes significant loss of life and livelihood. And the next year we have droughts that is in the way that we cannot even produce enough food for population. And that can be probably blamed on global climate change. However, lack of integrated and science-based management in the country exacerbate the impact of the climate change. So, for instance, there is no mechanism in place to use the excess water that we have in the wet season and use it for a season that we don't have water and droughts happen. And also, water has been used incorrectly in different sectors. For example, I recall from my own childhood that I grew up near the farm that people use this old techniques of inundating the entire agricultural land for producing food. That is the worst practice probably among all, that result into loss of water in the form of runoff and evaporation. And also it impacts actually the quality of the crop. So we often result into producing less food because too much water is not good for crop. And fast forward decades later, still the same practices are done. So everything has changed. The population has grown. We need to produce a lot more food. Water is short and scarce in many places. And despite all of that, still the old practices, all the approaches are used, which is inefficient and result into loss of significant amount of potable water that could be used otherwise for economy, agriculture, and also municipal.
Right. Yeah. So a lot of the changes going on, and I guess I spoke with Kaveh Madani earlier on another podcast from the UN, who he also grew up in Iran, and emphasizing, the big increase in population, about 20 million in the 50s to currently about 90 million, and a large increase after the revolution in 79. So that following decade, there was a big increase in population. And then, with the sanctions, then they need to have national food security. So, and then a lot of the people are involved in agriculture. So they need to maintain the agriculture for political stability and things like that. So a lot of forces coming together. And I guess, the source of the water for irrigation is important also to consider. And I think they've built a lot of surface reservoirs, about 90 cubic kilometers of surface reservoir storage now. So they store a lot of water in surface reservoirs. So if you're irrigating with surface water, like in California, sometimes they like to flood those fields in the winter to recharge the aquifer. But if you're irrigating with groundwater, then you want some very efficient irrigation system to try to minimize groundwater depletion. So do you think there is much surface water sourced irrigation in Iran, or is it mostly groundwater?
Right. So the approach that implemented in Iran, again, they used the technology and the mindset of 78 years ago, where we did not know anything about climate change and we didn't have the perception of the weather extremes, which we know them very well existing and becoming more frequent. So as a result, many of those dams built in area that nowadays they don't even receive enough surface water to accumulate that. So there are many dams in Iran that are dry. So the reservoir is below the bare minimum that to allow for even a regular discharge to provide water to downstream. So that's one problem we have in Iran when it comes to dams that are placed in wrong locations. And at the moment, they are not as efficient as they were supposed to be. The other issue that we have with dams is that many of those dams are, surface reservoir in general, are subject to evaporation. So large volume of the water behind those dams is evaporating before actually being used. That's changed the climate locally, but also it means that quite a bit of the water that we were hoping to have, it's not stored. And then maintaining dams is very complex and expensive task that, again, is not possible in Iran because many of the resources are actually redirected for other purposes, some of that political and military, but also mismanagement of the funds. It's a daily exercise in the country, and it's no surprise to me. And the other really issue is that, again, a science of how to use water, whether it's groundwater, surface water, has not been developed, or better say, is not adopted in practice. So we have very knowledgeable people inside and outside the country, including Kaveh, a good friend of mine, that have the right knowledge and adequate knowledge of that they can share. But usually those people are sidelines, and operators of the dams and those who are at the decision-making role, they usually don't have the adequate knowledge. For example, that simple exercise that you mentioned, irrigating land in winter to potentially replenish aquifer, is very effective. It's proven in California and many other places that has been extremely useful exercise to store some of the water on the ground and replenish aquifers. But it's not done, again, in countries like Iran. Either it's not done at the scale that is needed, or it's not done at the right time, or sometimes they don't even have the knowledge.
Right, right. And so I was reading a recent paper, and I don't know how to pronounce the author's name, Hadiji or something to that effect.
Hakshanas.
Pardon?
Hakshanas.
Factionals. Okay, right. He published a paper last year on the impacts of depleting aquifers and land subsidence in Iran, and showing, areas of subsidence about 3,000 square kilometers with greater than 10 centimeters a year, and some local areas up to 37 centimeters a year, about a foot a year, and suggested, I guess he was able to invert to the land subsidence data then to estimate the groundwater depletion, and he estimated about 1.7 cubic kilometers per year, and mostly in irrigated areas. And for US people, 1 cubic kilometer or 1 million acre feet is equal to 1.2 cubic kilometers. So they're similar. It seemed like in his map, a lot of the depletion was in the north, in those regions. Of course, maybe you can give us a little bit of background on the physiography of Iran, and where the deserts are, and you've got all these mountains surrounding area feeding into these aquifers. Some of that sort of background, Manoo.
Right. So there are two major mountain ranges in Iran. In the north, we have Alborz, and in the west and northwestern part, we have Zagros. So depending on where you are located with respect to this mountain range, you may receive a lot of rain, or you may experience actually very semi-arid to arid region climate. So if, for example, north of Alborz, it's some of the very wet states, provinces exist, such as Gilan and Mazan, and on those receive significant rain, and they are very green. And I will get back to that depletion of the groundwater, because unfortunately, depletion of the groundwater is almost decoupled from the climate surface. And then in the south of Alborz, we have several major deserts, very hot and dry. And that's where a large population of the Iran lives. For example, Tehran, Mashhad, Isfahan. There are three major cities in Iran. All three are located around or at those major, very hot, dry and semi-arid desert. And then to the west of the Iran, on the western side of the Zagros, we have also climate that is wet, but not as wet as the north, and it's colder, relatively speaking. And they receive a lot more snow in terms of precipitation than rain. So major aquifers that are depleted in the country are south of Alborz and east of Zagros. So when you look at the distribution of aquifers that are depleted, majority of them are in the central of the country towards southeast and eastern and southern part of the country, which puts you south of Alborz and east of Zagros. And that's also where we have large major cities, as I mentioned, located. However, we have many depleted aquifers in the northern part of the Iran, north of Alborz, and also west of Zagros. That's not intuitive, because there we get a lot of rain and a lot of snow. You expect there is abundance of surface water, so we don't need to deplete groundwater. However, again, back to that, what I mentioned, due to the mismanagement of the surface water and lack of infrastructures to treat that water, often that water drains into the seas in the north and south. So locals and also economy, industrial agriculture, again, receive very little portion of that precipitation. And they rely, again, heavily on groundwater that's extracted from the aquifers. So for that reason, entire country, even though some parts are wetter than others, experience depletion of the groundwater resources on an accelerated rate and in alarming fashion.
Right, yeah. And so the subsidence that this paper emphasizes, is very important for infrastructure and rail lines and roads and all of these sorts of things. And it even mentions moderate levels of subsidence near Tehran. So it seems like they need to be careful, if you're trying to address these issues, then so maybe not have much irrigation in critical areas and just restrict it to more rural settings, even though most of the subsidence is in rural areas.
It has been, but over the time has been growing so much that, for example, large part of the Tehran, the capital city, at least in the south, west and western parts, are on the subsiding aquifer. Some areas subsiding at a rate as fast as 20 centimeter per year. And this again is not limited really to the rural area and agricultural land. Even in cities, there are, I believe, some of that are illegal wells. Not all of them are permitted, but there are a lot of wells that tap into aquifers and for municipal use that may not actually have permission to
Right. And
right.
what was the rate you were mentioning there in parts of
So
Tehran?
the rate at different location varies. So some areas about 20 to 25 centimeter per year in Tehran, and Varamin, which is also western part of the Tehran, and there is another city called Karaj, also that experiences 20 to 25 centimeter of the subsidence, mainly due to groundwater extraction.
Right. And you mentioned early on, Manu, about wet and dry climate cycles. Some years you've got a lot of flooding, and that's a big issue also because a lot of mortality related to it. And then other years, then you have droughts, and we have the same here in the US. And I think some people say, we're running out of water, and other people say we're not managing the extremes. So it's challenging for the people everywhere to try to manage these extremes. I mean, you're in California, even this winter, atmospheric rivers, and they've had long-term droughts, and you've done a lot of work there, and then they'll have a family of atmospheric rivers. So I guess Iran is facing the same things, and what you're suggesting then is if we could take advantage of the wet years and store it underground to minimize evaporation, and then have it available then during drought.
Right. I'm a big advocate for managed aquifer recharge. I think that is a path to harness power of nature, because we at the global scale, when you look at the cycle of the wet and dry season, you might be right. There is not much change in it. So overall, at the global scale, we don't see much change in wet season and dry season. But when you look at climate region, so you can see that the peak maximum and peak minimum in the dry and wet seasons are deviating from each other. So when they enter a wet season, usually it's wetter, and when they enter a dry season, become drier. So one traditional approach has been to build surface reservoirs. You change the local ecosystem. You create a hazard, because every dam that you build at some point gonna fail. They are not destined for to stand there forever. So they have a nominal age. We can add to that few decades by maintenance, but eventually each dam can fail, which unfortunately we have evidence of that. Example of that happens in the United States, but also around the world, that during the extreme events, major dams failed and resulted in significant casualty. For all those reasons, and also, of course, cost. Dams are very costly infrastructures to build and maintain. For those reasons, putting water underground when we have too much of it with minimal treatment, I think that's really a futuristic solution for emerging problem. In a sense, futuristic, not that we don't have technology. By that I mean that is a solution that has to grow to adapt to the emerging hazards that are becoming more intense in near future and going forward. And Iran can benefit from that, USA and everywhere else.
Right. I think traditionally, a lot of funding for the water programs came from the World Bank. And, you can see a surface reservoir, you can see a dam, it's visible. And so they could relate to that. But storing water underground, it's a little bit more of a stretch for people. Will it be there when they need it? How much of it will they be able to recover after putting in so much? A lot of these basic questions. But I think we're slowly coming to the point that we're more comfortable and we have more information and more data to support it. I mean, if you look at the global scale, I mentioned earlier about 90 cubic kilometers of capacity for surface reservoirs in Iran. So globally, there was about 10 cubic kilometers per year of managed aquifer recharge. So we're at the early stages, and I think we're starting to do more and more. So Manu, you and your group have done a lot of work in California. And, we've seen a lot of subsidence in California over the past decades. And you've applied a number of different techniques to quantify subsidence in different parts of California. Maybe you can describe some of that work and what you learned, what the tools were, and what you learned from the output.
So we use mainly satellite data. Chief among them is radar interferometry, spaceborne synthetic aperture radar to be exact. So it's a technology that uses a microwave signal. So these are pulses of the energy transmitted from the satellite, hit the ground and bounces back to the satellite. And satellite, by collecting these return signals over the course of time, few years, and by comparing them with each other, we can measure changes in elevation at very high precision and accuracy in a line of sight of the satellite, which later it can be converted to vertical motions. And as a result, using INSAR, we can create larger scale map of vertical land motion across California at resolution of few tens of meters with accuracy of 1 millimeter per year or even better. So this is a revolutionary technology that allows us to detect many motions, many deformations that we didn't know even existed before that. So if put it in the context, GNSS, Global Navigation Satellite System, or in the past used to be called Global Positioning System, has been also used to measure crustal deformation. So we have a few thousands of them across California, but when you look at the distance between them, on average 25 kilometers, while with INSAR, we measure motions that are pixels that are tens of meters apart from each other. So we have orders of magnitude increased in resolution, which means our data we collect has increased in terms of value and also importance by order of magnitude. So by combining those data together, we are measuring geometrical change at the surface of the ground, which later we can associate that to change the groundwater using mechanical models. So there are models that link change in the fluid pressure under the surface and the elastic skeleton type of the rock to the surface deformation. So using that inverse problem, we can resolve volume of the groundwater that's changing on the surface and also how it's evolving over the time. So this is one set of technologies that we use. But also we use GRACE satellite, which is another spaceborne technology which measures changes in gravity field. So when mass of the water, or any kind of mass, not only water, it could be ice or could be also soil and sand, when the mass at and near the surface of the Earth changes, it has a tiny signature in the gravity field. That is very small, but thanks to this technology that is built, that became so precise and so sensitive, there are satellites that flying in orbits several hundred kilometers above the surface can measure those tiny changes in the Earth's gravity field. And then those changes can be converted back to the total mass of the water that has been added or removed to the system. Of course, this difference between GRACE measurement and what we get from INSAR is the spatial scale. So GRACE measurements, the nominal resolution is about 300 kilometers, as opposed to INSAR that is maybe 30 meters. So this difference in resolution provides challenges, but also opportunities. With GRACE, we can measure total mass change at a global scale every month. If we want to do that with INSAR, we need massive data centers that probably would not ever become available to us. ChatGPT probably would be priority there. And measuring the water availability on Earth. But with Gray satellite, we can access those information in timely fashion, which is extremely valuable.
Right, right. So as you say, all these new tools have revolutionized how we can monitor the land surface and the INSAR data. I mean, providing such high resolution data and high spatial and temporal resolution. So I guess is that Sentinel-1 data that you're using for INSAR, and that became available mostly through the European Space Agency in the mid 2015 or 2016.
Yes, so Sentinel-1, which went through 3 satellites already, A, B, and C, provided data going back to mid 2014 for in almost at the global scale. And this data is free of charge, available to anybody who can just go to the website and download data and use that for all kind of scientific, engineering, and other application, which has revolutionized our understanding of Earth's system. Not only changes at the surface, but also what happens under the surface and above, near the surface.
Right. And so California is really a poster child for this. And the U.S. Geological Survey and Claudia Font, who I spoke with before, they have been monitoring changes, subsidence, and Michelle Sneed at the USGS in California have been monitoring subsidence for decades, and others at the USGS. And so it's very interesting. It seemed like, early on, there was a lot of subsidence, a lot of groundwater overexploitation. That they built the canal systems, the State Water Project and the Central Valley Project to bring water from the humid region in the north to the Central Valley region. And so then most of the subsidence really, there was very little subsidence and the surface stabilized. And then more recently, they're seeing subsidence again. And I thought it was interesting. Michelle mentioned that, with the INSAR data, they found areas that were subsiding that they weren't aware of from ground-based monitoring. And so that was really cool. I forget the names of the towns and stuff that they found that there was subsidence, local subsidence.
There are many of them. I don't know which specific one she has mentioned, but there are many. That's a fun thing, actually, about INSAR. I process data randomly over at places. We have all this infrastructure ready. So as a hobby, I just choose a place and I process data, which is automated with AI and everything. We do this on cloud. And I always get surprised. I've been in this business for almost 15 years and still I get surprises every day. So for just that reason, INSAR has revolutionized, has nurtured our curiosity in a way that no technology could do that. I'm each data sets, I'm always curious what I see, what is new that I didn't know. And we learned so much about it, so much new stuff from this data. So, and I think the INSAR technology is that it's in infancy yet. So much bigger development and innovation will happen in the decades that is ahead of us. Thanks again to AI, because very often we just cannot mine the data, the volume that we produce. We don't have time to sit down and look at every pixel. Thanks to artificial intelligence and all this sophisticated tool, we are automating the examination of the data that is produced using INSAR. And that helps us to identify signals that we went unnoticed because just a large volume or, the operator, the person who was examining data missed that. And I think there will be a lot of new discoveries, things that I believe surprise people down the road.
Right. See, you guys, your group published a very nice paper in 2018 in Water Resources Research on groundwater loss in the Central Valley. And how it was amplified by the drought. I think you were referring to maybe the 2007 to 2009 drought. And there you were recording, almost a foot a year subsidence in the Tulare Lake Basin, but much less subsidence in the north in Sacramento. And then you were able to compare with GPS data, several hundred stations, and also with groundwater level data. I think the results from that showed about, 7 cubic kilometers per year of depletion.
Right.
And for example, maybe Texas uses about 20 cubic kilometers a year of water. So that was a lot of depletion. And maybe you can describe a little bit, Manu, when you have groundwater overexploitation, how it relates to depletion in unconfined and confined aquifers, and when you lower the head or the water level below the consolidation stress, some of that sort of thing.
Sure. So that study was very interesting because I believe that was the first valley-wide study that leveraged existing satellite data to study the entire Central Valley as a whole. Because Central Valley is massive, so it's extended over hundreds of kilometers from the south to the north, and it crosses through different climates. South is essentially dry and or semi-arid region, while in north we have more precipitation and cooler weather. But that is the type of the crop is also different, and type of the water exploitation and so on. So we were interested in that study to look at the whole, create a holistic picture of the entire Central Valley. And we were lucky that the drought of 2007 through 2009 was covered by that ALO satellite, which is a Japanese satellite operated at L-band. We processed all those data and we extracted the vertical land motion for the entire valley at the pixel size of few tens of meters. And then one thing that we did there, we tried to extract elastic from inelastic deformation of the aquifer. So elastic deformation is what happens, at seasonal scale. So, when you look at the water head levels or even time series of deformation, you see those seasonal variations. Those are usually elastic response. We don't expect much inelastic deformation from in a year-to-year changes. But when you look at the long-term trend, some areas you mentioned, 20-25 centimeter subsidence, which is mainly associated with the decline water level or head level inside the confined aquifer. That can be alarming, specifically if water table drops below the previous lowest level. And that's we call pre-consolidation level. So if the head level drops below the pre-consolidation level, naturally it cannot be recovered. So if you do, you can recover that through, for example, hydraulic fracture. But if you just don't want to apply any excess pressure, similar to what is done in fracking, naturally those level, the volume storage for the period of time that head level dropped below the pre-consolidation level is lost. So that's what we call inelastic deformation of the aquifer. And that's alarming because inelastic deformation over the time effectively it means that aquifer cannot naturally store water. So, of course, fraction of that, the percentage that we estimated was small. It was 1 or 2% of the total storage capacity of the aquifer. But no, again, we come back to this discussion we had at the early part of this podcast. Extreme events becoming more and more frequent. Since the beginning of this century, we had 2, maybe 3 very, very dry droughts in Central Valley. Scientists and authorities categorize them as one of the worst in millennia. So, and if we lose that capacity, storage capacity through inelastic deformation, during each of these extreme events, each time we lose maybe 2%. By end of 2100, and by end of this century, if the trend continues as it was, Central Valley probably would not be able to store more than half of what it stores today, Central Valley aquifers. And that has implication for agriculture and agricultural practices that is done in the valley that rely on, for example, groundwater for irrigation.
Right. Yeah. And the Central Valley is a fairly unique system. I mean, it's a very thick aquifer, several kilometers thick. And, a lot of those sediments came off the mountains, the Sierras and the coastal range. So you've got this big, thick alluvial basin, but you've got a lot of fine grained sediments in it also, like the Corcoran clay and some other clays. And so it's the depletion in the confined part of the aquifer that's linked to subsidence and those dewatering clays. And then some of that is permanent, so permanent loss of storage, and so you cannot recover it. I think Claudia Font estimated, looking at 1960 to 2019, about 160 cubic kilometers of depletion of groundwater over that time, and estimated about 15% of that storage loss was permanent.
Permanent, yes.
So that's a very important. And you've also done work in Arizona, around the Phoenix area. And that's a very interesting area because they're really the active management area. And so they brought in the Colorado River water, and so they switched from groundwater pumping. They didn't switch from groundwater pumping, but they were able to add water from the Colorado River through these spreading basins. And so your work there, you showed some areas where the land surface was rising and other areas where it was declining and subsiding. And so maybe you can describe that a little bit, Manoo.
Yeah, Phoenix is a very interesting case because, they have history of land subsidence in 3 locations. One is in north of the city near the area called Scottsdale. One is to the east of the city at Apache Junction, and one is to the western side. Those are sites of the rapid subsidence historically at the fast rate. Present day rate is as fast as few centimeter per year, but they have seen the rates that were faster than 10 centimeter per year. So then they decided we want to stop that, and they thought a lot about that, and they came up with the idea of recharging aquifer. And for some reason, they chose the center of the valley as a recharge site. So, and they have some wells that inject water underground, but also they have recharge basins that they flood them and let the water seep into the ground. And so the idea was that we put the water there, and eventually, hopefully, water migrates where land subsidence has happened, and it compensates that some of that loss, and eventually land would rise there, or at least slow down the land subsidence. What happened in practice is that the center of the Phoenix Valley is rising now because, of course, it takes a very long time. Sometimes water flow under the surface is not what you hope for. It's not doesn't go to the location that you anticipated. So for that reason, we have 3 zones of subsidence in the Phoenix Valley, in the perimeter of the city, and at the center of the valley, we have a zone of uplift that is tied to the recharge site. So, land subsidence is a hazard for infrastructures, but uplift can be equally bad. Linear infrastructures would be affected by uplift as much as they are affected by land subsidence, but also it impacts drainage networks. So in most cities around the world, drainage networks are built to follow the effect of gravity. So when you pour water on the ground, it just follows the gravity until it drains the streets and eventually make it to either the sewage network or nearby open lakes or water bodies. So when you change the elevation artificially, those drainage may not work. So this problem is not as dominant in Phoenix Valley, but I have another example, Houston, Texas, that effect of the change in elevation on the drainage network is so severe that after each hurricane and heavy storm and rain, majority of the Houston city remain flooded for days, sometimes weeks after the hurricane, just because drainage network is no longer able to drain the city because of change in elevation.
Right. And you bring up a good point, Manoo. When I think about California and the Sustainable Groundwater Management Act, and I was talking to Tim Parker recently from California, and he mentioned that subsidence may be more of a constraint than water use for the region, and that people using the water may be held responsible for subsidence. And so that gets quite complicated, I think, because I mean, you can have a lot of residual long-term subsidence. When you were talking about Phoenix, I think the uplift was about 0.6 centimeters a year, and then the declines maybe 1.5 centimeters surrounding areas. But so, I mean, it would be difficult. And I think when we spoke previously, you mentioned that insurance companies don't cover subsidence, and it's a difficult thing to quantify. I mean, you were making a lot of progress, and then to attribute it to an individual and their practices might be very, very complicated.
Very challenging. We know the land subsidence is a slow-growing hazard, and it will impact infrastructures, it impact economy, various industries. In California, they have problem with expansion of this high-speed rail because of land subsidence. We know it's there, but first of all, assigning a dollar amount to the cost of land subsidence has been a challenge. So there has been some work on it, but still it's not in a way that is reliable, and also it's not verifiable. So, for example, we assign a dollar amount to land subsidence today, and often the argument is that this land subsidence, if continues over the next 10 years, that would be the cost. And we don't know if it happens or not. And then we don't know how area of land subsidence evolves and how it stops and how other factors would impact us. For that reason, inserting land subsidence in any policy decision proven extremely challenging. So we know that it exists. We know it's a challenge to every engineering project, but we are still not there to quantify it in a way that is verifiable and also actionable.
Right. And I think in California, the Central Valley, you mentioned about the drainage networks in Houston, but also the aqueducts in the Central Valley are being impacted by subsidence and stuff. And I think that's a big concern.
That's correct. Yes. Yeah. It's costing. We know that aqueducts are affected by that. It is costing a lot for maintenance and repair. But again, it's very difficult to convince. If somebody wants to deny that, they have a way out.
As you say, it's difficult to verify. And the other area, Manoo, that you and your group have done a lot of work on is subsidence along coastal zones. And these are extremely important. And I gather from the papers that you have published is that people are not paying enough attention to subsidence. There's a lot of emphasis on sea level rise and things like that, but maybe not enough emphasis on the vertical land motion and the subsidence in coastal zones and how that could be amplifying the impacts of sea level rise and underscoring the importance of relative sea level rise that considers both the land subsidence and the sea level rise together. Maybe you can describe that a little bit, Manoo.
Right. Historically, when it comes to coastal hazard or coastal processes or coast as a whole, of course, it's where almost 65% of the world population lives within hundreds kilometer stripe along the global coast, and almost 15% of the population live within area that is less than 10 meters above the sea level. So a large portion of the world population and important assets and infrastructures are exposed along the coast. However, historically, when they talk about coast, the view was from the lens of climate change. Climate change causes the expansion of the ocean because of the warming and also melting of the ice and glaciers that is added to the water, and sea level is rising. So, but when we approach the problem, we look at it from the perspective of an end user, the stakeholder, a person, a homeowner along the coast, a utility manager or a commander of a military air force base that is on the coast, we realize that what matters to them is not sea level rise, it's a relative sea level rise, meaning relative change in elevation of the land and sea. So if you keep the sea steady, somehow you manage to stop the sea from rising. Still, if the land elevation drops, the impact is the same for them. They get flooded, the infrastructure experience failure, corrosion, water, salt water enters the aquifer. So we approached the problem from perspective of the end user when started quantifying vertical land motion along the global coast. And we learned that in many places that people live, I want to emphasize that at a global scale, sea level rise still dominates everywhere. But when you look at where people live, that's where there is a socioeconomic importance. Mainly, land subsidence by order of magnitude is faster than sea level rise rates. So, in other words, for cities along the coast, the majority of the hazard within the next few decades is driven by change in elevation of the land subsidence, rather than sea level rise. If we go beyond 2050 to the end of century, probably scenarios would be different. But until 2050, our study and analysis shows that many places land subsidence is the dominant factor when it comes in coastal hazards such as flooding, saltwater intrusion, and also degradation of the infrastructures.
Right. And so, your analysis looking at the US, then you looked at the Atlantic, the Gulf of Mexico, and the Western US. And so there were quite big differences regionally between vertical land motion among those different regions. Maybe you can describe that a little bit, Manu.
Right. When you look at the entire US mainland coast, we see three different regimes, so three different regions: East Coast, Gulf Coast, and West Coast. And they are very different in terms of geology as well. So, West Coast is rocky because of this faulting processes of subduction, while East Coast is the passive margin, sandy and very flat. And then Gulf Coast is where we have lots of oil and gas resources that has been exploited for many years. Some of the fastest land subsidence on the planet actually is associated with the extraction of the groundwater, oil and gas in, for example, Goose Creek oil field in south of Texas that goes back to 1920. So having that all included in our consideration, we found out that the fastest rate of land subsidence, present-day land subsidence along the U.S. coast happens in Gulf Coast area. Cities like Biloxi, part of New Orleans, experience the fastest rate of land subsidence, some 4 or 5 times faster than sea level rise. And then the second place goes to East Coast, where we have a combination of the glacial isostatic adjustment effect. Northern part of the United States, northern part of the American continent and also Europe was covered by a thick layer of ice almost 15,000 years ago, which has melted since. As a result of that, entire Canada is rising at a rate of almost centimeter per year, and the perimeter of that, which is mainly United States, is subsiding at a rate of 1 or 2 millimeter per year. So East Coast of United States is specifically experiencing land subsidence due to the GIA, and at locally groundwater extraction and also partly groundwater extraction of the oil and gas would contribute to faster rate of land subsidence along the East Coast. So some areas such as Chesapeake Bay experience about 5 to 6 millimeter per year of the land subsidence. And then at last is the West Coast of United States. It's rocky. There is very little subsidence due to extraction of the fluid. Even the fluid extraction happens, but it's not as widespread along the West Coast. And we see that rate of land subsidence on the West Coast is not as much. So we have some area like San Francisco, the reclaimed land in San Francisco that are subsiding at a rate of about 1 centimeter per year, but majority is about 1 or 2 millimeter per year.
Right. And I was looking at the plot that you had in that publication, and some areas in the West Coast are actually rising. I forget which of those
Two
locations.
sites are rising. One of them is Santa Clara aquifers, and the other one is Santa Ana. And both of them are the success of the managed aquifer recharge that managed to, those were textbook example of land subsidence until 1970 and 80. And since then, a specific Santa Ana aquifer system, despite ongoing droughts, they keep it level or even slightly rising, which is fascinating.
Right. And I guess that's near LA.
Yeah,
And
yeah, south of LA, yes, Orange
right.
County. Yeah.
And so they're doing a lot of managed aquifer recharge there. That's interesting. And you mentioned Louisiana and Texas parts. I mean, Biloxi, about 6 millimeters per year of subsidence there. And so it seemed like there needs to be a lot more emphasis on subsidence and at least especially if it's happening more in the heavily populated areas. And in that analysis, you estimated, the areas that would be flooded under different future climate scenarios and stuff. And I guess that is if you don't have any sort of structures to protect the areas. And so
Yes, we
now
call
I
them
think,
undefended scenarios. Mhm.
right. And I guess, Texas is considering the Ike Dike as a structure to protect the coastal areas. And also Louisiana has done a lot of work
Sure.
in trying to do that. But you mentioned Katrina, sometimes these structures fail and then that could be even more catastrophic
Yes.
when that happens.
Unfortunately.
Yeah, yeah. And you mentioned earlier, artificial intelligence helping you work with all of these data. So you have a lot of different data sources. You will have INSAR data, you have GRACE data, huge differences in the spatial resolution and how much data you're dealing with, and also more localized data from GPS. And can you describe a little bit how you're using AI to fuse all these different data sources and
Right. So one thing I realized over the course of years is that one main reason for inaction is the scale of the problem. So when we talk about land subsidence and people look at these maps, they see land subsidence everywhere. Bridges are subsiding and house and building and dams and cities and so on. And when you look at the scale of the problem, you realize that you need so much money, trillions of dollars, if you want to address the problem at once. So, and that often become a reason, oh, we don't have the money, we can't do anything. So we thought about it. So we spent some time and thinking how to go about it. And I noticed the healthcare system, insurance system. So, when I, pass a certain age limit, so I have to go more often to doctors, to general doctor, physician, to see if there is anything wrong. So often I go there to check the numbers, nothing happens. And then sometimes, the numbers don't look good. They send me to a specialist, and that specialist may do something or say, no, don't worry about it, and then go back to that cycle. So we thought that we should implement the same approach to deal with the land subsidence impact. So instead of highlighting the problem from perspective of land subsidence, highlighting it from perspective of vulnerability of the targets that is affected by that. A young person has a different need than, for example, a more senior person, right? So AI help us to do that. So we are developing AI tools that help us to prioritize, for example, infrastructures when it comes to land subsidence, based on the type of the infrastructure, based on the age, based on the exposure that they had. So AI would help us to tell which infrastructure should receive the attention first, which one can wait another 5 years, 10 years, and then later. So in this way, instead of coming up with the astronomical number at the beginning, we come up with a very reasonable number that can be put in any budgets. And then, okay, this much money you need to deal with this issue at this time frame, and then next 5 years you need that and that. And that's one of the many applications of the AI that has been really revolutionizing the way that the topic of risk risk of land subsidence has been addressed and from political perspective.
And then what AI tools are you using to do that, Manu?
So we've developed some in-house. We use convolutional neural network and some others. Also some simpler one. Random forest and things like that. And we create objectives that those objective function has parameters related to, for example, type of the building, high rise, low rise, type of the construction material, age, and then rate of land subsidence. And then we create, using that data-driven techniques, AI, we create scenarios of the future land subsidence, elevation change, how that would impact different infrastructures. And we translate everything to a cost. What is the cost of the repair? What's the cost of replacement? And so on. And then that would give us data that is associated with the scenario. So, of course, we cannot tell what happens in the future, but we say that if you follow this scenario, this would be the outcome.
Right.
And those scenarios will be presented to, policymakers, operators, and then based on that, they make decision. In fact, we're creating now something we call it decision theater. That's powered by all those AI and digital twins, and you can sit and just on the fly change the parameters and see how the future, costs would change. For example, you can say that, we want to use Y amount of groundwater instead of X amount. So using those models that we built, physics-based but also AI, we can estimate what would be the associated vertical land motion, what would be impact on the infrastructures, what would be cost, etc., etc. And then this would provide you with the data that you can use for any kind of decision making that you have to do in real time.
Right. Yeah. I mean, that's amazing. And I think some of the advantages of AI are that you can combine many different types of data. Traditionally, with our, modeling in the past, we were limited to looking at the hydrology or the this or that and independently. But now with AI, I think you can bring in all of these together and do it at a speed, and allow people to test things, which is and use as much data as possible. Is there anything else you would like to share on the podcast, or do you feel like we have covered most of the things?
We covered a lot of good things. Thank you so much, Bridget.
Yeah.
It was fun. It's really fun. Thank you very much. Appreciate
Well,
that.
our guest today is Manoo Shirzaei, and he's an associate professor of geophysics and remote sensing at Virginia Tech. And the topic has been land subsidence and its importance from semi-arid regions where we've got groundwater overexploitation and fishing and Central Iran, Central Valley, California, Arizona, and then also coastal areas and its importance for relative sea level rise. Thank you so much, Manoo. I appreciate it.
Oh, thank you so much for having me.